Welcome to the next video of me relearning Maxwell's equations. We're into chapter 2, Gauss's law for magnetic fields. This is from the book, A Student's Guide to Maxwell's Equations by Daniel Flesch. Okay, so the chapter 2, it starts out with the integral form of Gauss's law for magnetic fields. And here's the first problem. Find the magnetic flux, keyword flux, produced by a magnetic field, thus through the top, bottom, and side surfaces of a flared cylinder shown in the figure. And here's the little figure he gave. So, full disclosure, this took me a while because I was overthinking this. In that I said, oh my, this is a flared cylinder. I'm going to have to integrate this. How am I going to do that? Well, I really overthunk it because the Gauss's law for magnetic fields, it tells me what to do. So, and like I've said before, if you look through the chapter preceding the homework, the problems, you will find something similar enough that you can do it. And as soon as I realized that with a magnet, so let's say there's a magnet here. So he's showing the magnetic field, just one piece of it, right? Well, Gauss's law says the magnetic field through a closed surface is zero. The magnetic flux through a closed surface is zero. So imagine there's a magnet here. Well, it's got a north pole and a south pole, right? They have to. So the magnetic field is going like this. It's looping around, going in and out of all these different surfaces, right? So I really don't have to worry about exactly what this is, just knowing it's a closed surface. The big hint is he gave us this radius, r top and r bottom, right? So if you look at this equation, you're saying, well, he gave us the magnetic field. What is this normal? The unit normal. Well, what is that? Well, the other hint is he gave you a coordinate system. He's got x, y, z. So that's I, j, k. So the unit normal on this one would just be up, right? And the unit normal on the bottom one would be down. So n hat on top is just k. N hat on the bottom is just minus k. So that was the first thing that I got straight. So now I can do this, right? So I can take the inner product of the magnetic field with the normal, which is just k. And that's obviously that k dot k is 1 and k dot these others is 0. So I'm just left with 4 from here. Integral of dA. Okay, so what's the dA? Well, he gave it to us. He said r top. So it's just pi r squared. So the first one is just 4 pi r squared. There's no need to do any integrals. Then the bottom is going to be the exact same thing, except this time the unit normal is sticking in the other direction, so it's negative k. You do the exact same the process, you get negative the 4 pi r squared of the bottom. And then here's the secret to solving the whole thing. I don't have to worry about the sides and that weird function that they have on those slopes, because the total flux is the magnetic flux going through the top and the bottom and the sides, and that all has to add up to 0 because that's the way the Gauss's law works. So all I got to do is solve for this by taking it to the other side, and there it is equal to 4 pi r squared bottom minus r squared top. Anyway, that one was harder than I thought it was going to be, but it was kind of fun. Now this next one is upsetting me, and I'll explain. What is the change in the magnetic flux through a 10 centimeter by 10 centimeter square lying 20 centimeters from a long wire? So he's given us a closed surface, 10 by 10 square. And he's given a distance here, r, from a long wire carrying a current that will increase from 5 to 15 to milliamps. So here he's given us a spread, okay? Assume that the wire is in the plane of the square and parallel to the closest side of the square. All right, so I drew a little picture here. So this is the current, right? So it's going in some direction 20 the centimeters away from a box that is 10 by 10. Okay? Now, in the chapter before the problem, I was trying to think, how am I going to envision this magnetic field? Well, it's really simple. It looks like that. So there's a magnetic field that's going in the right hand rule with respect to the current moving. Okay. So in our little the picture, this magnetic field is looping around like this, going in and out of the box, right? And the box is a closed surface. So we know that part. So here is what we've got to solve. And I said, well, what's this? I don't know what this is going to be because there's no mention of what the field is. Well, in the chapter, and the reason this bothers me is he gives this table. Magnetic field equations for simple objects. Infinite straight wire carrying current I at distance R. Boom. There it is. Well, where's that come from? I looked through the chapter, and there's no mention of it. So I looked it up on the internet. This is derived from Ampere's law, which we haven't got to yet. How's I supposed to know that? And also there's I think that's a phi. I don't know what that is. A phi hat here. Well, what's that? What's that phi hat? Where'd that come from? What's it mean? Well, he doesn't explain it in the chapter. I found one example where he says, oh, here's my integral. And he says, in this case, the unit normal is equal to negative phi hat. Why? Where'd this come from? I hate stuff like this. I want to know where this comes from. I want to know why this is true. I couldn't find it in the chapter, so I'm just going to use it. And in our case, so the problem is this is turned out to be positive. And I can't explain why. I don't know. If you know, please tell me. All right, so here's what we know. We got that from this table. This comes from God. We don't know where this comes from. And we know that the unit normal is equal to this phi hat. All right. So to get on with progress, we just use it. So we put it in our integral, and phi hat dot phi hat is obviously 1. So we got this, and now we've got a current here, and we got this distance here. We know that distance is going to be x, because that's the way we drew our the problem here, right? This is x and y. So we know that part. So, and what is our dA? Well, that's also as obvious to me, is that we got dx and dy, because this is just a box, dx and dy. So that's our dA. Now, what are our limits? What's the limits of this integral going to be? That took me a little longer, but I kept staring at this little diagram from the book, and it come to me. This magnetic field is going in and out of this box, right? So we want to integrate from here, y equals 0 to y equal 10. And we want to integrate from x equal 20 to x equal to 30. Now, these are in centimeters, so to make the problem work out with units, you have to change those to meters, which I did not do the first time, and I got a really stupid answer. Then I come back and said, oh, all right. So we got, this is a constant here, except for I, but we're not going to integrate it. So we have an integral of y from 0 to 0.1, and we got an integral of x from 0.2 to 0.3. So that's that x part of the box. Okay, so the integral of dy is just y. You take the limit, you get the 0.1, so we got a constant. The integral of dx over x is ln x, and we're going from 0.2 to 0.3. All right, so we do that math. It turns out this constant here is 4 pi times 10 to the minus 7. That's what an unusual constant. So the pi's, the cancel, we bring the 2 out, so we're left with just a constant times the current. Now, the question was, what is the change in the flux as the current goes from 5 to 15 the milliamps. So we just take a delta, right? So we put in our 5 in amps, we calculate, put in our 15 in amps, we calculate, we just take the delta. Okay? So that's the answer. In whatever these units are, Webers or, yeah, they're WBs, whatever that is. So anyway, I did not enjoy this problem because I don't like being given something like this and not know where it comes from. And 10 minutes later, I'm going to forget. Well, if I don't derive this, I won't know what it is 10 minutes from now. Anyway, onward and upward. All right. Thanks for watching.